Okay, ready? Three, go. Good day, everyone. We are Group 2, and today we will be presenting our laboratory number 3, which is the operational amplifiers. Next slide, please. For our team, we have Abela Cassandra May, Bianzon Janric Ivan, De La Cruz Maria Clariz, Hermoso Crystal Phoebe, and Rueca Julius. To introduce our laboratory, operational amplifiers are essential components in analog electronics because of their high gain and versatility in signal processing applications. This experiment focuses on assembling and testing inverting and non-inverting amplifier circuits to compare theoretical and actual performance through measurements of voltage gain and frequency response. The activity also helps develop practical skills in circuit construction, troubleshooting, and understanding the effects of non-ideal operational amplifier behaviors in real-world electronic systems. Okay. Here is our objectives. First is to calculate the gain of a different configuration of an operational amplifier. And next is to understand the operation of an operational amplifier. Here is our materials. First is the adjustable DC power supply, function generator, resistors, operational amplifier, oscilloscope, and simulation software, which is in this our case we used Multisim.
For the procedures of the non-inverting amplifier, construct the circuit shown in figure 4.1 given the data in table 4.1. Apply sinusoidal input to the amplifier. Refer to the table 4.1 for the frequency, positive 15 volts 2 and negative 15 volts 2. For each combination of and input voltage frequency, measure each output voltage and compute its gain. Find the maximum peak-to-peak output voltage by varying the input voltage without distortion for each frequency. This procedure is performed to observe how the circuit amplifies signals without changing their phase and to analyze the effect of resistor ratio and frequency on amplifier performance. Next slide. For the non-inverting amplifier, for each input voltage and frequency, measure each output voltage and compute its gain. Find the maximum peak-to-peak output voltage by varying the input voltage for each frequency. Compute using the equation 4.1. This procedure is conducted to verify that the voltage follower maintains a gain close to unity and acts as a buffer circuit for impedance matching. Next slide po. And for the inverting amplifier, construct the circuit shown in figure 4.3 given the data in table 4.3. Apply sinusoidal input to the amplifier, positive 15 volts 2 and negative 15 volts 2. For each combination of and input voltage frequency, measure each output voltage and compute its gain. Find the maximum peak-to-peak output voltage by varying the input voltage without distortion for each frequency. This procedure is intended to study signal amplification with phase inversion and to analyze the relationship between resistor ratio, gain, and frequency response.
For the moving on to the page 9 and page 10 of the PPT, these pages shows our data and results for part A, which is the non-inverting amplifier. First, since the non-inverting configuration, our input signal is connected to the positive terminal of the op-amp, as we observed in our simulation. The output voltage is in phase with the input voltage. This means there is no phase shift. The waves move in the different direction. Second, let's look at the relationship between the resistors and the gain. The formula of the theoretical gain here is 1 plus Rf all over Ri. Lastly, we tested the circuits across different frequencies from 10 Hz up to 1 MHz. To summarize, the data on these slides validates that our non-inverting amplifier successfully amplifies the input signal, which keeping it in phase. And our simulation results closely match our theoretical computations.
Then for part B, we evaluate the voltage follower configuration, which is operate as unity gain buffer where the output signal directly mi- mirror the input voltage. Our experiment result the valid this behavior demonstrate the high stability voltage gain. While this specific circuit configuration provides no voltage amplification, its performance confirmed that our practical application for isolation of impedance matching unit ultimately this ensure excellent signal integrity. Next, please. Next is the part C. We evaluate the inverter amplifier configuration, which is scaled to the input voltage while introducing standard shape phase shift. Our data show that the feedback resistor increased relatively input resistance. The voltage gain increased proportionally according the formula. The circuit demonstrates the stability of linear amplification across the frequency range up to 1 MHz, providing the operation amplifier perform reliably within the physical bandwidth. Next.
Now, for the analysis, the experiment verified the operation of the inverting operational amplifier, where the voltage gain depended on the resistor ratio and the output signal was inverted by 180 degrees. The circuit showed stable performance at low frequencies and input voltages, while distortion occurred at higher values due to op-amp limitations. Overall, the measured results closely matched the theoretical calculations. In conclusion, the experiment successfully demonstrated the functions and characteristics of operational amplifier circuits, including inverting, non-inverting, and voltage follower configurations. The measured results closely matched their theoretical values, confirming the principles of voltage gain, phase relationship, and frequency response. Overall, the activity improved understanding of op-amp behavior and developed practical skills in circuit constructions, testing, and troubleshooting. So that would be all. Thank you.